In this lesson, we learn how to construct the confidence interval to estimate a parameter. Previously, in the point estimate, we give a single estimate for a parameter. A single estimate could change when we have different data collected. When new data is collected, we will not know how good is the estimate from a single reported estimate. So instead, we would like to use an interval to give a plausible values of a parameter. That gives the confidence interval. The construction of confidence interval generally will involve the distribution of a statistic, and that often relies on the central limit theorem that we have learned in earlier chapters. So we'll first briefly go over the central limit theorem, and then afterward we learn how to construct the confidence interval for one population mean. And we will also try to see what kind of factors affect the confidence interval, including the width of the interval, and also if we want to have a desired width of the interval, what sample size is needed to guarantee that. First is a review of the central limit theorem. For the central limit theorem, that basically talks about the distribution of the sample mean or the total from a simple random sample. Let's say x1 through xn records the simple random sample from a distribution, and the sample has mean of mu, and the standard deviation is sigma, and we know the sampling distribution of x bar, and the total is Sn is approximately normally distributed when the sample size n is large. And this requires the population variance to be finite. Whenever n is large, the sampling distribution, regardless of what is the actual population distribution, whether it's symmetric or skewed, we can use the normal to approximate the sampling distribution of this sample average whenever n is large. And the sample mean x bar would have the distribution centered at mu, and the standard deviation equal to population standard deviation divided by the square root of sample size. And in terms of the total, the summation Sn, if the sample size is large, this Sn is also approximately normally distributed, and its center is n times the mean of one variable, so it's n mu. And standard deviation is simply the square root of n times the standard deviation. That's for the large sample size. If the sample size is not large, or so in some cases, if the sample size is not large, in that case, we would quite often assume that the population is normal. So if the population is normal, that means that x1, x2 through xn has normal distribution with mean mu variance sigma squared. If that's the case, then the sample mean x bar and the summation, the total, both of them will be exactly having normal distribution, and we do not have any approximation needed. So their distribution would be exactly normal regardless of what is the sample size if a population is the normal. The central limit theorem basically says that if we try to consider the x bar, how far is it away from the population mean, then we can use this probability to quantify that. X bar minus mu divided by sigma square root of n, this ratio tells us how many standard deviations away from the mean. If we put this consider just within one standard deviation around the mean, then that probability is going to be around 0.683. So one standard deviation. for X bar, the sample average values within one standard deviation around the mean, that part captures about 68.3% of the probability. And if we change the range to be from 2 standard deviations, so the X bar could deviate from the center mu by 2 standard deviations, so taking k equals 2, then that becomes 95.4%. If we take the k to be 2/3, in that case, what we have is 50% of the data is in the middle. Similarly, when we consider the total, if we use total minus the n times mean divided by square root of n and sigma, this also states how many standard deviation is the total away from its mean. And this has the same probability. Both of them are actually, both of the ratios are the z-scores. That's stating how many standard deviations the quantity is away from its mean. So if we use this negative k and positive k here, we basically gives a bound for this ratio to be between a certain to be within a certain probability, and then from there we can get the interval about the mu. So that's basically the idea. So the idea is that use the central limit theorem. If we use the mean plus minus 2 standard deviation of this X bar, we will have about 95.4% of the sample mean in there. But it's not the sample mean that we are interested. Instead, what we are interested is the population mean mu. So we will try to rewrite this inequality X bar in between the lower bound and upper bound, and instead we'll try to subtract the X bar on every side in this inequality, the 3 sides. So we'll have a negative X bar here and a negative X bar in the middle and negative X bar from the last right-hand side. So the one in the middle, when we subtract the X bar, it becomes 0. And then, so left-hand side becomes the mu minus X bar. Right-hand side is also mu minus X bar. The next is that we're going to subtract mu on every side, and then we will remove the mu, and then mu becomes the center here. Negative mu between these 2 bounds, and then we multiply by -1 and switch the direction of the inequality. Then what we get is that this mu is between the X bar plus or minus 2 standard deviations of X bar. That gives us the same probability of 0.954. So this roughly tells that if we have this procedure to collect the data, and then we can tell that such data, we use the calculated X bar minus 2 standard errors of the X bar, we will have a 95.4% of the chance to capture the mean. So this interval would be the 95.4% confidence interval. But unfortunately, the sigma is unknown to us. If that is unknown, we could not really compute it. So the SD, standard error of X bar, will have to be replaced by an estimate of that. Sigma is the standard deviation. In the point estimate, that chapter, we learned that sample standard deviation can be used to estimate the population standard deviation. So we will replace the sigma by the sample calculated standard deviation. Here's that formula for the sample standard deviation. It simply is the sum of squared division, and they divide by the n-1. That n-1 is the degrees of freedom, because when we have originally x1 through xn, that's n of those values. All n of them are free, but once we compute the average to estimate the common mu, with that average, we no longer have n free values, because all of them add up, divided by n has to be equal to the average. So only n-1 of them is free. That gives the degrees of freedom n-1. And for this standard deviation, it is computed from the observed data xi. So if we do the experiment at different times, multiple times, we can expect the calculated standard deviation using this formula would also be different. So it is a random variable tool, just like the X bar is a random variable. Once we have the standard deviation to estimate the sigma, we can proceed with our confidence interval procedure. But before I move on here, this is some fact that's worth to mention. This is called the law of large numbers. If we have a random sample x1 through xn from a population, this random sample generally can be written as like IID, means identically distributed independent data from the same population. And if the standard deviation is a finite number, in that case, we would know for sure that this average from the computed sample would approach this true population mean, even though we do not know that. And the standard deviation computed from the sample will approach the population standard deviation if the sample size is getting large. So because of that, the population mean and population standard deviations generally will be actually estimated with the X bar, and the sample standard deviation estimated the population standard deviation, as long as the distribution is not too skewed and the sample size is not too small. Okay. So earlier we mentioned that the sample standard deviation can be used to estimate the sigma. Therefore, the standard deviation of X bar, which is sigma over square root of n, can also be estimated with by plugging in the estimate of sigma, which is the sample standard deviation. This SD is the sample standard deviation, and then divided by square root of n. SD can be computed from the data. If you have the numbers available from the data, simply assign those numbers to a variable and use SD parentheses those numbers that will compute the standard deviation for you. And once we have that, you use that SD divided by the square root of n, give us the standard error. And this standard error is an estimate of the actual standard deviation of the X bar. So after we have the standard error, now we can use this X bar plus or minus the two standard error to give us that interval. And that interval would be still approximately having probability of 95.4% if we have these X bars collected from the sample repeatedly. So basically, as the sample size gets large, we already know this X bar is approximately normally distributed, and then this the X bar standard error will become smaller and smaller because of the sigma over square root of n. So the square root of n in the denominator. Therefore, this interval will become smaller and smaller, the narrow, as the sample size n is large, because the standard error has square root of n in the denominator. And we call this X bar plus minus 2 standard error as the 95.4% confidence interval. And this interval is because our sample is random, so it has this probability of 95.4. So in the next few slides, we will also still assume that the sample size n is large enough so that we still can use the central limit theorem to help us construct the confidence interval. When the n is smaller, in the later lectures, we're going to learn another different distribution, t distribution, that will help us to construct the confidence interval. So we have learned this two standard error around the mean that give us the 95.4%. And now consider, instead of the 2, what if we replace the 2 by another value? Say, for example, if we use a percentile from the normal distribution, if we use 1 minus alpha over 2 percentile, then what will happen is that this is going to give us consider the X bar. plus or minus, so x bar minus mu divided by standard deviation within this z of 1 minus alpha over 2. That probability is 1 minus alpha because the center of that is 1 minus the tail. Each of the tail is alpha over 2. So the center of that is the 1 minus alpha. So if we put in there, that's when it gives us 1 minus alpha probability. And from there, if we arrange the inequality, we're going to get the mu between x bar minus or plus the z times standard error of x bar. So that's a confidence interval with the confidence level of 1 minus alpha. So compared to the 95.4% confidence interval, the change here is that this percentile is used rather than the 2. So what percentile do I use? For example, if I want the 95% confidence interval, this alpha would be 5%. So the z 1 minus alpha over 2 is the 97.5 percentile, which is 1.96. And this x bar plus minus 1.96 standard error would give us the 95% confidence interval. So in general, if we want a 1 minus alpha confidence interval, we would use x bar plus minus this percentile 1 minus alpha over 2 percentile from the standard normal and then times the standard error divided by square root of n. And this is assuming the n is large enough. This formula, if we want to compute it in R, we could actually just think of it as x bar being the center, and from the center we'll move to the left by the z times sd over square root of n, and also move to the right the same amount. If you compute it in R, because x bar is the center, so you can think of that this is the distribution from the normal quantile, use the Q norm with the x bar as the mean, and then the SD or square root of n as the standard deviation. Okay, so here's the R code. Suppose you are given the x bar from the data, and you want to give a confidence interval. In that case, this 1 minus alpha confidence interval. You first need to compute what is alpha. For example, for 95% confidence interval, alpha is 1 minus 0.95, which is 5.05. So you assign alpha equals 1 minus 0.95. Okay. Once you have the alpha, then the next is to write down the x bar. Originally, it was plus minus the normal quantile times s over square root of n. But since the two of the, if we go back to look at the two, one is the negative the z normal percentile, the other one is positive normal percentile. For the normal distribution, we know that it's a symmetric distribution. The 1 minus alpha over 2 percentile is the opposite of the alpha over 2 percentile. So basically, this left-hand side, negative z with 1 minus alpha over 2 is simply just z of alpha over 2 percentile. That's why we can use this plus sign and then put the alpha over 2 to get the quantile. And the other side is the 1 minus alpha over 2. And that formula is also equivalent to simply think of it as the normal quantile centered at x bar. So we use Q norm here with these two proportions, and then we specify mean as x bar. As C use the S over square root of n will give us the correct computation tool. So that's if you have you were given the sample mean and the sample standard deviation, and you have a large n. In some cases, you have access to the actual data. If that's the case, let's put the data in X And we can just simply use a t-test with x in there and specify a confidence level equals the number. For example, if we want a 95% confidence interval, we would do the t-test x and comma and CONF that level equals 0.95. If you want a 99% confidence interval, change the CONF that level to 0.99. This is assuming that n is large. And if n is not large, in that case, in the later part of the lesson, you will learn that we need to assume that data comes from normal distribution, and then this t-test would still be valid if the data comes from normal distribution. After you check the normal, say if you try to do the normal quantile plot and you find that the data do not seem to be falling on the straight line in the normal quantile plot, and that tells that normal distribution is not plausible, is not suitable for the data, in that case, we'll have to consider an alternative non-parametric procedure to construct the confidence interval or do a test. Here's an example for the confidence interval. For this example, we consider a delivery company in New York City that they want to estimate the mean delivery time to any place in the city. They have a randomly selected sample of 50 deliveries that gives an average delivery time of 2.8 hours and a standard deviation of 0.6. So that's saying that n is 50 and x bar is 2.8 and s is 0.6. We want to estimate the mean delivery time to any place in the city with 90% confidence. So this one is asking for a 90% confidence interval, and we have summary data. So as we have learned, we can simply use the Q norm with the two of those proportions and use the mean as the x bar as the mean and s over square root of n as the standard deviation. So we do x bar equals 2.8, and then with a semicolon here to separate the different assignment, different command. So the next one, s equals 0.6, and so on. And the alpha here is always the 1 minus confidence level. And then we put in the Q norm with the remaining part that gives us the confidence interval. For the confidence interval, you see 2.66, 2.93. That's a pretty small interval. Simply means that the estimate is pretty accurate. This interval is small, it's narrow. So that's the confidence interval, 90% confidence interval. If you want to consider 95% confidence interval, then what need to change is simply this 0.9 here will need to be replaced by 0.95, and everything else will stay the same, and the output will be different. That's the confidence interval, example 1. Here's the next example. Called, we want to consider the mean number of count trees per acre in a forest. They have a 2,000-acre plantation, and a random sample of 50 of the plots is selected and examined. The average number of count trees per acre is 27.3. and standard deviation of 12.1. Use this information to construct a 99% confidence interval for the mean number of count trees per acre for the entire plantation. So what we have here is a sample with sample size of N50. We can just use the formulas directly compute the confidence interval. So we put in all these numbers. X bar is 27.3, S is 12.1, and the alpha here is 1 minus 0.99. And then we use the Q norm with the two of the proportions. One is alpha over 2, the other is alpha 1 minus alpha over 2. And then we use the X bar as the center of this distribution, and SD is S over square root of n in the Q norm. That'll give us the confidence interval. So based on this observed data, we would say that 22.89 and 31.71 is the 99% confidence interval for the mean number of count trees per acre. So that's the confidence interval computation. And here's the third example. For this example, there are 37 stations, and they were trying to consider, this is for in-soil water in Kenya, and they wanted to see the lead concentration in it. And we have the sample contains 37 stations, and we want a 95% confidence interval for the mean lead concentrations. Okay, for this one, 37, that's not very large, but it's still just at the boundary between large and the small. We'll have a quick look at these numbers. These numbers seems to be different quite a lot. Some are single digit, like 7 or 9, 6, and some are very large, 210, 112. So in that case, the first thing is better to try to do the plot. On this slide, it shows the plot that we're giving is a histogram rather than the QQ norm. The histogram with 37, 37, even though it's bigger than 30, but it's not too large, so it is a good idea to have a look at the distribution to see how skewed it is. In the QQ norm, we can assess whether it comes from normal distribution or not, but it's difficult to judge about the skewness. That's why here a histogram is shown. So you first collect the x values separated by comma and assign it to x, and then afterward directly call the histogram of x that will show the histogram. In this case, because of the two large values, 210 and 112, here I'm also considering to remove those two values. So how do I remove? I use the set difference. And x is the originally observed sample, and I put the 210 and 112 in there in the set difference that will remove those two numbers and then recompute result the histogram. Beyond that, this slide, also the last line, shows theta test with the x in there and confidence level 0.95. So let's look at the output. First of all, this one also shows a box plot. I did not show you the box plot command. If you do want the box plot, simply just call box plot with parentheses x there. So that gives box plot. It clearly shows the two outliers, the 112 and 210. And when we look at the histogram, it's skewed, obviously skewed. And the last, the rightmost histogram shows when the 210 and 112 being removed. The net distribution is still skewed, but not as much, not that too bad. And we had a sample size of 37. With 37, we do not really need to require the population distribution to be symmetric normal, but we need it to be not too skewed. So in this case, because with the 210 and 112 in there, the distribution is quite skewed. So in fact, we need to be skeptical about the result obtained from this theta test. So in this case, give us confidence interval of 24.8 and then the 49.6. This interval is relatively wide, also partly because of this deviation is large and it's skewed. In fact, for this data, it's probably better to use a non-parametric method that we'll introduce in chapter 15. Okay, so we learned how to construct the confidence interval. This next part, we will learn how to interpret the confidence interval we obtained. This interpretation of confidence interval comes from the probability assignment. When we try to consider the confidence interval, we actually use the probability for on the distribution of x bar, the sample mean. And this, for example, in the 95% confidence interval, we had this x bar plus minus 1.96 as our square root of n. That's an interval which has the probability when the X bar is unobserved and X bar itself will change from sample to sample. So with this interval, we can say that we are 95% confidence interval. We are 95% confident that the mu will fall between these two, the X bar plus or minus. But this X bar so far is still just a random quantity. It will change from value to value, from one set of data to another set of data. But what if we have the data already collected and we computed the sample mean? For example, in the earlier example, we had the X bar, such as in this case, the X bar was given to be 27.3. If you already have a 27.3 and this interval already computed, 22.8, 31.7, in that case, do we still have the probability in there? With a single interval and the X bar already computed, then this interval would either contain the true mean or not contain the true mean. There's no more probability associated with that interval. So interval has probability only when we have the X bar being random and that changes from one sample to the next sample. So when we say the 95%, it's really talking about such interval, a large number of such intervals. Okay, so what is random is this X bar and also the standard deviation of it. And hence the interval would be a random interval. And for this interval, it changes from one data set to a next data set. In other words, if you construct the interval 100 times using 100 different data sets, it will have 100 intervals and they are different. So what's going on is that one of the interval might contain the true mean or not containing the true mean. And what actually is really doing is that you have so many of them, but you can tell that around 95.4% of them will contain the true mean. So that's basically the nature of the confidence interval. It's not correct to say that, for example, let's say probability of mu, like for example, a 95% confidence interval is constructed and gives the lower bound 0, upper bound 4, and then you simply say that the probability that mu is between 0 and 4 is 0.954. That's wrong, because the mu itself is not a random variable. It is a fixed quantity. There's no probability associated with a fixed quantity. So instead, this probability has to be associated with different samples. So once you are looking at just the mean itself, the mu itself, for example, the mu, if it's actually 1.7, we don't really know, we don't really have a probability of 1.7 in 0 to 4. Similarly, and in other numbers, like between 1 and 3, you also don't have a probability for mu in there. So instead, for any of the interval that has already been computed, like 0 to 4, then this mu is either inside of that or it's not inside of that. So how do we actually interpret this confidence interval correctly? We would say like this. It's really considering like as if you have parallel universe and you are computing just one of them. And suppose we repeated the confidence interval computation infinite many of times, and each time you collect a data set of the same sample size n, and then you compute a 95% confidence interval for each of the data set. Eventually, out of these many data sets and the computed confidence intervals, you're going to find that around 95% of them will contain the true mean. And about 5% of them, the true mean is not inside of there. That's from a large number of such experiments. This interpretation is due to the interpretation for the probability, which is based on the large number of experiments. So in general, the confidence interval correct interpretation would be that you can say we are, for example, 95% confidence that such constructed interval will contain the true mean, but we never put this interval on one single we never put this confidence on just one single interval. So here's an example. Let's say here we want to consider a commercial process that produces shrimp for sale to restaurants, and shrimps are monitored for size by randomly selecting 40 shrimps and measuring their length. We do not really know the true mean and standard deviation of the shrimp, and we would try to construct the confidence interval for the mean. In this case, let's say what I wanted to do with this example is to show you what will happen if you have large number of samples, and for each sample, you compute the confidence interval. So what I'm going to do is not you do in practice, because in practice, you don't have this large number of samples. Instead, you are going to have only one sample. So do not repeat what I'm doing here. Instead, here, I'm going to tell you the fact. Suppose if I actually able to obtain 1,000 samples, and these 1,000 samples are all from normal distribution. And suppose that I'm drawing the sample from normal with the mean 27 and standard deviation of 10. For these 1,000 samples, each one of them, I take its 40 shrimps, and so basically sample size is 40, and I want to compute a 95% confidence interval for the mean. Since I'm going to have 1,000 intervals, I will check each of the intervals to see whether my mean 27 is inside of there or not. So for this experiment, I do have the truth. The truth is that the mean is 27, and I have 1,000 samples. So what I'm trying to see is that these 1,000 intervals, how many of them contain the true mean 27? Here's a table of some of the intervals. Like the first one gives sample mean, first sample gives sample mean like 26.73, and the lower bound of the confidence interval is 23.98. And the next one, upper bound gives 29.47. I'm sorry, this is the same confidence interval. If we look at the lower bound, upper bound, and our 27 is inside of there, therefore this interval contains the mu. So you see true here says the mu is inside of that interval. Similarly, for the next interval and so on. Keep going for all 1,000 of them, you will see some of them do not contain the 27 in it. This red colored, that's one example that did not contain 27. So out of the 1,000 in this experiment, what I get is about 95.5% that contained the mu 27, and the remaining 4.5% did not. So this is from 1,000 samples. Generally, if you have a large number of large number of samples and compute confidence intervals, you can expect around 95% would contain the true mean if you constructed the 95% confidence interval. So that helps you. I hope this helps you to understand the meaning of the confidence interval is for a large number of experiments, and the procedure of confidence interval construction is repeated, and around 95% of them will contain the true mean. So here, if I'm able to put all of them there together, like here shown, what I show is just 100 of those, so that they're not too cluttered for us to see. Each of these with the two of the dots represent the interval. Like for example, this red one starting with around 20 and end around 26. This is the lower bound, upper bound of the confidence interval. And this red one did not contain 27 in it. 27 is this line in green colored. So if any of these interval did not cross this 20 with the 27, then that interval did not cover the mean 27. So you can imagine that if I draw all these 1,000 of these, roughly it would be about 5% of those are the red ones that did not cross with 27. Okay. So that's the interpretation of and how to construct the confidence interval. In the next video, we'll try to consider a special case, the confidence interval for proportion. And that will simply apply this confidence interval procedure to the estimating for proportion case. So we'll stop here for this video.